All right, welcome back, everyone. So today we should be able to finish off this chapter and then spend the next couple of days after that then doing the next chapter for the upcoming exam on Monday. So just remind you what we talked about last time. So again, we said that we have the electric field. So the electric field is defined as, again, in this context, the limits as the test charge goes to 0 of the force per unit charge. Of course, you can also just simply write it as F over Q, assuming that this charge is pretty small, that it is a test charge. So literally, again, what this thing says is that the electric field then would be the force that a charge would feel at a given location due to the presence of some sort of electric field. For specifically a point charge, what we found then was that the electric field at some given point r, distance away from that point charge, is simply equal to kq over r squared. Whether it's capital Q or little q, it doesn't matter. Sometimes I write it as capital Q, sometimes I write it as little q. It's the same thing. And then superposition principle says that at any given point in space, then the total electric field at that point is simply equal to the vector sum of all the electric field contributions from all the individual charges that are creating an electric field disturbance. So now let's start off with here. So this thing says that, again, the electric field then is the force that a charge would feel at a given location if I put a charge there, or basically meaning that what? That if I know the force, I can then find the electric field by simply plucking out that charge, right? But this thing actually says the converse as well. What this thing says also is that, well, if I know the electric field at a given point, I can then easily find the force by simply multiplying the electric field by the charge. So this actually works both ways. So this says, if I know the force, I can find the electric field, but if I know the electric field, I can also simultaneously find the force. Okay. So that's what we're going to concentrate on right now. So this thing also says that if we know E at a given location, then we can determine the force on Q. So this is another statement that this expression actually says. So again, it works both ways. It says if we know F, we can figure out E by simply plucking out Q, or if we know E, we drop in Q and then we find F. So that's pretty much it. So all this means then is if we know the electric field from some sort of charge configuration, whether that's a point charge or a bunch of point charges, or some of the things we looked at yesterday, like an infinite sheet of charge, if we know that exists, then all we have to do then is drop in a charge, and then we can find all the force on it. Once we know the force, we can find the acceleration, and etc. So let's look at a couple problems of this and see how this guy actually works. So the first one we're going to look at is we're going to take a charge, in this case, capital Q, and we're going to send that in between two what are known as parallel plate capacitors. And we'll spend some time in the next couple of days talking about capacitors, what this is. But what a parallel plate capacitor is it is two plates separated by some distance where the two plates both have charge to them, but one is positively charged and the other one is actually negatively charged. But they have exactly the same magnitude of charge. So meaning if this top plate has a charge of, say, plus little q, then the bottom plate has a charge of minus little q. And these guys are separated by some distance of, let's say, d. Now, what we're going to do in this case then is, as the problem is basically saying here, we're going to take a charge particle, which has a mass of m. So this is, say, my charge particle sitting at this point, has a mass of m and has a charge of capital Q, and we're going to send it in between these two plates with some initial velocity v. So let's say here is my charge. This thing has a charge of q, but a mass of m. And let's say initially this thing is going to move in between the two plates with some initial velocity, and let's call this guy v0. Now, as long as it's outside of the plates, what happens in this case then is we're going to pretend that all the electric field only points from the positive plate to the negative plate, because we now know that the electric field points from a positive charge to a negative charge. That means the electric field then is going to point like this inside of the plates. So this is going to be our electric field. We're putting in this section out here, it's 0, even though, as you actually saw from lab, it's actually going to bend around to do something like this, but we're going to ignore this. This is what's known as edge effects. So we're going to say it's in between the two plates. Now, what's going to happen then is what? As this guy starts to move inside of the plates, by the time it interacts with the electric field, it's then going to feel a force, right? So meaning that, let's say our charged particle now moves to this location here. What's it going to feel? Well, we know from this guy, what this says then conversely is that the force is simply equal to the charge times the electric field. So in this case then, since the charge is positive, the electric field is downward, that means this guy is going to feel an electric force, or that electric force then is going to be downward. So this is going to be the direction of the electric force. Which means that this guy is going to accelerate in the direction of the electric force, because Newton's second law says that force and acceleration are the same thing, right? Just multiplied by a mass. So whatever direction it feels a force has to be the same direction as the acceleration. So what's this thing going to do? So what it's going to do is it's going to move in, it's going to feel a force downward, which means this thing is going to end up doing what? So moving this direction, but feels a force downward, what happens to it? It's going to curve under parabolic motion. Exactly. So what's going to happen then is that this charged particle, as it moves in, initially will move straight, but then will start to curve. Right? It's going to do something like this. This is the same thing as what? Little g acting on this eraser as I throw it across the room. So in this case, little g pulls down in this direction, velocity is that way. So eventually it starts to curve downward. Right? Glad I missed Sam. Sorry about that. Okay. Is okay. So it curves down because it feels an acceleration downward. So it's going to curve down like this. Now, our job then in this problem is to say, well, if this thing came in on this line, so if it had no acceleration, it's going to move in a straight line. But since it gets deflected downward due to this acceleration, now the other thing to note is once it moves outside of the plates, it's then going to move in a straight line again. So the velocity afterward will be in this direction, right? Since there's no acceleration after that, it's going to move straight downward. So what we want to know is, by the time it comes outside of the plates, by how much has it been deflected in the vertical direction? If these plates have a length of, say, L to them. Now, for now, I'm going to work with just saying this is an electric field, and we'll talk about what the electric field actually happens to be. But let's just kind of work with this guy. So good. So we know then is that what? This guy is going to be deflected vertically downwards. I'm going to choose a coordinate system. I'm going to go ahead and say that in this direction, the direction it was originally traveling is my x direction. And I'm going to go ahead and say that downward is my positive y direction, since that's the direction it's being deflected. So cool. So if I want to know the amount of deflection, I'm going to use my second kinematic equation, which says that what? My change in y is then going to be equal to the initial velocity, in this case in the y direction times the time, plus 1/2 the acceleration times the time squared. Is okay with this? Just second kinematic equation from last semester. Now, according to our picture though, what's the initial velocity in the y direction? 0. Good. So we know this first term is just gone. Since there is no velocity in the y direction, it's only in the x direction. So this is then just going to be equal to, well, 1/2 the acceleration times the time squared. Now, where's the acceleration going to come from? Well, we now know that the force that this thing feels is simply equal to the charge of the charged particle times the value of the electric field. So that means in this problem, we know the force is then just going to be capital Q, since this thing has a charge of capital Q, times the magnitude of the electric field, which we're going to call E. Now, Newton's second law says the sum of the forces, which in this case is simply that force of F, has to be equal to what? Mass times acceleration. So we know then that this must be equal to ma by Newton's second law. So what does this tell me? This tells me then that the acceleration this guy feels is simply going to be the charge times the value of the electric field divided by the mass. This is the acceleration on this guy. So this then says that I can write this as 1/2 the charge times the electric field divided by the mass, all times the time squared. So this is my amount of deflection. So this says I can find this amount of deflection here, delta y, if I know the amount of time that this thing spends with inside of the plates. Do I know the time it spends with inside the plates? Offhand, no, but where am I going to get it from? What was that? Exactly, that's true. And why is that true? So let's start off with a basic expression. So let's go back to our kinematic equation, our second kinematic equation, now in the x direction. What's true about the acceleration in the x direction in this case? A very specific constant. What constant? 0, right? So what we can do in this case is we can use the x direction. So we can say that the change in position in the x direction is equal to the initial velocity in the x direction times the time plus 0, because there is no acceleration in the x direction. In this case, the initial velocity in the x direction is simply equal to the initial velocity that this thing had times then the time of t. Good. So what this says then is by the time this thing gets deflected the amount of delta y, this thing has traveled the entire length of the plates, which is exactly what Caleb said. So if I want to know what the time is when this thing comes out of the plates, all I then have to do is say, well, this thing traveled the total distance of the plates, which is L, divided by the initial velocity, and then that's the time. Exactly what Caleb said. So let's do that. So what we know then is that this thing is going to travel the total length of the plates, L. So this time then is going to be equal then to L divided by the initial velocity, which I can plug into here, which finally gives me that this is 1/2 the charge times the electric field divided by the mass, times then the length squared divided by the initial velocity squared. So this is the amount of deflection. Now, the last thing we have to talk about here is what's the value of the electric field? Now, there's two ways I can know the value of the electric field. The first way is I could explicitly tell you in the problem, inside of here, there's an electric field which has some magnitude to it. That's one way. The other way is, since this is a parallel plate capacitor, and I know the charge here and I know the charge here, we can use the fact that a parallel plate capacitor is actually just two infinite sheets of charge separated by some distance of d, which means yesterday when we wrote down that the value of the electric field above an infinite sheet of charge was equal to what? Sigma over twice of epsilon naught. That means inside of the plates, we're just going to have simply twice of that value. And why do we have twice of that value? Well, we have twice of that value because this one, we know the electric field points radially away like this. For this one, the electric field is pointing radially inward like this, which means here this value has an electric field of sigma over 2 epsilon naught. This also has a value of sigma over 2 epsilon naught. Since I have this guy in, this guy added together, that's a value of sigma over epsilon naught. I have two values of that. But notice on the outside, if I stretch this guy in this direction, this electric field here is actually opposite to the direction of this electric field. And if I did the same thing down here, if I stretch this guy up to here, this electric field here is opposite the direction of this electric field. So actually it turns out for parallel plate capacitors, the electric field here and the electric field here are 0, where the electric field on the interior is simply twice of that of a sheet of charge. So the electric field out here is equal to 0. Electric field out here is also equal to 0. So the electric field on the inside is equal to sigma divided by epsilon naught. So the final thing I'm going to do is just replace that over here. So this is finally going to be equal to 1/2 the charge of the charged particle times the charge density of the plates divided by the mass times epsilon naught, all times the length squared divided by the initial velocity squared. So this is my deflection between the plates. And remember that sigma, based on what we talked about yesterday, is the total charge per unit area. So this is the charge per area, also known as the surface charge density, which has units of coulombs per meter squared. Who's okay with this? Then let's do another example. 7, yeah. So this one is basically the same thing, but a little more complicated, because now what's going to happen is this charged particle is going to come in at an angle. So it's going to come in at an angle here of 45 degrees relative to the horizontal. Okay. Comes in with an initial velocity v0, which is 6 times 10 to the 6 meters per second. The length of the plates here is equal to 10 centimeters. The separation between the two plates here is what? 2 centimeters. And this has an electric field, which is pointing upward, which has a magnitude of 2 times 10 to the third newtons per coulomb. All right. So meaning that this is the positive plate down here, this is the negative plate, because we always point from positive to negative. Now what I'm going to do is I'm going to shoot an electron inside of here. So what does that mean? So that means if my electron is, say, sitting here, this is feeling a force, right? Because again, we know the force is simply going to be equal to the charge times the value of the electric field. Now, what's important about the sign of a charge of an electron? Is it positive or negative? It's a negative, right? So if I multiply a vector by a negative, what does that do to the direction of the vector? Exactly, it rotates about 180 degrees, which means in this case, since this is an electron, the direction of the force will not be in the same direction as the electric field, but it's going to be in the opposite direction as the electric field due to the fact that it's a negative charge. So what's going to happen is the electric field is going to come in, but it's going to feel a force downward. It's going to cause this guy to curve. Okay? Now, what we want to know, the first part of this question is my electron going to get curved enough that it's going to miss the top plates, but be curved too much that it's going to come down here and hit the bottom plates? Or is it not going to be curved enough, so it's going to come up here and hit the top plates? Or is it just going to make it all the way through? So what we want to know is this thing curving not enough and hits the top plates, too much hits the bottom plates, or is it just fine? Then once we know if it does hit a plate and which plate it hits, where does it hit relative to this location here, which we're going to call, say, x is equal to 0 location, meaning that if it hits the top plates, how far away from the edge does it hit the top plate? If it hits the bottom plates, how far away from the edge does it hit the bottom plate? So these are the 2 questions we need to ask. And I'll use this eraser since I threw the other one across. So let's draw the picture. And talk about how we know which plate it actually hits. So here is my top plate. Here's my bottom plate. In this case, we know, again, our electric field is pointing this way. We know the magnitude of the electric field is 2 times 10 to the third newtons per coulomb. Here is my electron. So let's say here's my electron. So here we know the mass of the electron is 9.11 times 10 to the minus 31 kilograms. The charge of the electron is equal to negative the fundamental charge. This thing has an initial velocity going in this direction. It's my initial velocity at this initial angle of theta initial, which is 45 degrees. And we know the initial velocity is, what was it, 6 times 10 to the 6th meters per second. Finally, we know that these guys are separated by distance of d, which is equal to 2 centimeters, and the plates have a length L, which is equal to 10 centimeters. So again, part A. Part A we want to know is, does it hit one of the 2 plates, and which one does it hit? Okay. So let's systematically kind of go through each one. Let's ask the question first, is it going to be curved enough so it misses this top plate? Okay, so let's see if it actually hits the top plate or not. Okay, so again, what I know is that once this thing's on the inside, let's say it's sitting here, again, we know the force is going to be the opposite direction as the electric field due to the negative charge, which means that the acceleration is going to be downward. So in this case, let's choose a coordinate system. I'm going to call this my positive y direction moving upward, positive x direction moving to the right. And the reason I'm taking positive y upward is because the initial velocity in the y direction is upward, even though the acceleration is downward. So I'll have to have a negative sign for the acceleration. But So how would I know, for example, if my electron hits the top plate or not? How would I know? Go ahead. Find its max height, exactly. So what's gonna happen is this thing is gonna move in, and then it's gonna undergo parabolic motion, and then it's gonna curl around and do something like this, right? Which means that what? The max height would be the point where this thing reaches max. So let's say this is my Y max value. Right? So as Preston is basically saying, if I can find what Y max is, if Y max is greater than the distance between the two plates, then that means it has to hit the plates. But if Y max is less than the distance between the two plates, it means it missed the plates. Right? So let's find out what max height is. So how would I find max height? You guys remember how to find max height from last semester? What had to be true at max height? Could do that. Could do that. Good. That's probably an easier way to do it. So what we know is that anytime I throw something into the air, well, I don't lose this eraser too. So when I throw it across the air, what has to be true is that by the time it reaches the maximum height, it has to momentarily stop, at least in the vertical direction. Doesn't mean about the horizontal direction, but the vertical direction. So what we're going to do then is exactly that. We're going to use the fact that at max height, this thing has to temporarily stop in the Y direction, use that to find the time, use the time then into the Y direction to find the max. Or we can do what you said, find out how much time it would take to start and finish at the same horizontal line, and then divide that by 2 and then put it that way. It works out basically the same. But let's do the max height one. So let's do, we know the velocity in the Y direction at max height has to be equal to 0. So let's remind ourselves of our first kinematic equation, which says that's what? The final velocity equals to the initial velocity plus the acceleration times the time, right? Now, in this case, since we chose our positive Y direction to be upward, we have to have a negative sign in here since the acceleration is in the opposite direction of the velocity. So let's write that. So this is going to be then equal to the initial velocity in the Y direction minus the acceleration times the time. I'm going to write this as T max, just so we don't confuse it with some other. Good. So what this says then is that what? T max then is going to be equal to the initial velocity, all divided by the acceleration. Okay. Sehr gut auf Deutsch. Okay. Great. Now what? Now we're going to plug that into our Y expression. So let's say Y expression, we know Y then, by the second kinematic equation, is equal to the initial Y position, which we can call 0, times then the initial velocity in the Y direction times the time, minus 1/2 the acceleration times the time squared, where again, the minus sign comes from the fact that acceleration is downward, where we chose positive Y to be upward. Good. Now here, Y max occurs when T is equal to T max. So all I'm going to do is plug in T max here. So I get Y max then is then going to be equal to the initial velocity times T max minus then 1/2 the acceleration times T max squared. Now let's plug in what T max is. I'm going to leave this in symbolic notation for now, and then we'll write out what all this stuff actually means. So I get a V0Y times a V0Y divided by A, right? It's easy one. Minus 1/2 A times this guy squared. So I'm going to get a V0Y squared all divided by A squared. Here I have a V0 times a V0Y times a V0Y. So what's V0Y times V0Y? V0Y squared, right? So I get a V0Y squared divided by A minus 1/2. Here I have an A divided by an A squared. Well, what's an A divided by an A squared? 1 over A, good. So then I get a V0Y squared divided by A. So good. So what does this say? This is basically what? X minus 1/2 of X. Right? But what's X minus 1/2 of X? 1/2 x. So at the end of the day, this says then that y max is equal to 1/2 of the initial velocity in the y direction squared, all divided by the acceleration. Now let's fill in some blanks. V0y is simply this portion of the initial y velocity, but since this is the opposite direction of this angle, this is just going to be the sine portion. So this is going to be equal to 1/2 the initial velocity squared times sine of 45 degrees squared, all divided by the acceleration. But we already know the acceleration from the previous problem, where the acceleration was equal to the charge times the electric field divided by the mass. Because the acceleration that we have here is exactly the same as the acceleration in the previous problem. There's nothing different about it. So I'm going to move the mass term to the top. And then I have what? So it's going to be the charge times the value of the electric field. In this case, we know the charge is simply the fundamental charge. So I'm going to replace Q here with little e. That's our fundamental charge. Okay. Now we're just going to plug in our values. So again, the mass here is the mass of the electron, so it's 9.11. We know the initial velocity is 6 times 10 to the 6. We know the angle is 45 degrees. We know the charge is the fundamental charge, which again is 1.602 times 10 to the minus 19 coulombs. We know the electric field value is 2 times 10 to the 3rd newtons per coulomb. So plug in all of that. What I find then is my stuff here, that this works out to be about 2.56 centimeters once I put it into centimeters. Numbers okay? So that says that that would be the maximum height that this charged particle would reach if this top plate didn't exist. Now, how far away is the top plate though from the bottom plate? 2 centimeters. So is 2.56 centimeters bigger than, less than, or equal to 2 centimeters? Bigger than. So is it going to hit the top plate? Yes. So we know in this case then it hits the top plate. It's okay. Yep. Oh, well, that's what we're going to find out now. So the next part of the question is, where does it hit the top plate? Right? Because 2.56 won't be great enough. But we're going to do that now, basically. So good. So now we want to know, just to make sure that this thing actually hits while it's inside of the plates. So let's make sure that actually hits by finding out the distance that it is horizontally away. So let's do that now. So good. So that's a great question. So now we want to know is, let's say it hits here. What I want to know then is, what is this distance here? Let's call that X hit. So what is that distance away from the left-hand side that this thing hits? Because I want to make sure it actually does hit on the inside. Because you could be right. It could be just miss the plates and then reach max height from there. So let's do that. Let's find out, what is that H? Good. So part B, let's go ahead and work with our second kinematic equation, again, which says that X is equal to the initial position, which we can call 0, times the initial velocity in the X direction times the time. And is there any acceleration in this problem in the X direction? No, all the accelerations in the vertical direction. So this thing says we can find out what X hit is if we know the time it takes for it to hit the plate. T hit. So now we need to figure out what's T hit. So where's T hit going to come from? Exactly. So now all we're going to say is, let's go back to our Y expression. But now instead of finding where it is when it reaches max height, now we know where it is, but we need to find the time where that time is then going to be where it hits. So good. So from our Y direction, we know Y then is equal to the initial velocity in Y direction time minus 1/2 the acceleration times the time squared. In this case, we know that when Y is equal to D, which is at 2 centimeters, that's going to correspond then to the time at which it hits. So let's call that T hit. minus then 1/2 the acceleration times t hit squared. Everyone's okay? From here, we just need to solve for t hit. So I'm going to rearrange this and make it look like an actual quadratic. So I'm going to add this term over here, subtract this term over here, set this thing equal to 0. So I get 0 then is equal to 1/2 a t hit squared minus the initial velocity in the y direction times t hit plus the distance of d. From here, I have to solve a quadratic. I'll just set up the quadratic. I'm actually going to solve it. But this says that t hit then is equal to negative b, which is going to be initial velocity in the y direction, plus or minus the square root of b, which is the initial velocity in the y direction squared, minus 4 times a, where a is equal to 1/2 the acceleration, times c, which is d, all then divided by twice of a, which is 2 times 1/2 the acceleration. Beautiful. Plug in my numbers, I get some time. Once I know that time, I can plug that back into my x expression here and then find what I need. And what I find in this case then is that plugging in this time into this expression gives me a total distance of 2.727. So what this says then is that what? This thing hits the top plate when it has only gone 2.72 centimeters away from where it came in. Since the total length of this is 10 centimeters, then yes, this happened inside of the plates. It didn't make it outside of the plates and just happened to reach max height after it reached the plates. It's okay. So again, the gist of all this is as long as I know what the electric field is, I can then find the force acting on a particle, i.e. the acceleration, and then I can just put it into kinematic equations and do whatever it is that I want from there. So as long as I know what the total electric field is, I can then find the force, or if I know the force, I can then find the total electric field. It works both directions. So great. So next thing we're going to talk about is, now that we know about electric fields, we can start talking about conductors a little bit more in depth. So basically look at what information do electric fields tell us about conductors. So let's go back to conductors. So we want to know, based off of what we now know about electric fields, what has to be true then about conductors? So the first thing we're going to say is, number one, if a conductor has charge to it, so meaning if I had, say, some sort of conductor, here's my conductor, and let's say I put some charge on my conductor. So this thing has a, I don't know, say total charge of plus Q. Now, since charges are allowed to freely move inside of the conductor, what has to be true then is that what? These charges, if I try to put them inside of the conductor, they actually have to spread out as far away from each other as possible due to this Coulombic repulsion, which means all of the charges will end up being exactly on the surface of this conductor. So what happened is if I dump a whole bunch of, say, positive charges on the inside of here, each one of these positive charges are going to feel a repulsive force between them, which means they want to move as far away from each other as possible, which means that this scenario then will go to this. So all the charge then will be found only on the surface of the conductor itself. This is the furthest that these particles can actually get away from each other. So the first part, all charge will be on the surface of the conductor, meaning that there'll be no charge on the internal of the conductor. So no interior charge. Now, as far as the electric field is concerned, what does that do then for the electric field itself? Well, what that means then is since all the charges on the surface of the conductor, so this thing is going to have electric field lines pointing regularly outward. Well, let's think about what's happening on the inside. So on the inside, I have an electric field line pointing in this direction, this direction, this direction, this direction, this direction, this direction, etc. But if I sum all of these guys together, what ends up happening then is that the electric field on the interior of the conductor must be equal to 0. All right. So at all times, the electric field on the interior then must be equal to 0. So number 2, the electric field is equal to 0 inside of the conductor. Now, of course, you may ask the question, what happens if I put a conductor into an external electric field? So let's say, for example, I have a electric field, say, pointing like this. Now I'm going to put some sort of conductor inside of that electric field. What happens in this case? Well, again, what's going to happen in this case then is that what? We now know that since there's an electric field, the charges inside of the conductor, because the conductor is made of a metal, right? So it does have charges on the interior of it, but there's no excess charge. Well, what happened is the positive charges are going to move in the direction of the electric field. The negative charges are going to move in the opposite direction, which means if I put a conductor inside of an electric field, what will happen in that case then is all the positive charges will build up on one wall. All the negative charges will build up on the opposite wall, meaning that the conductor itself will create its own electric field, which points from the positive charges to the negative charges, which will end up being the exact opposite as this external electric field. So this will be the electric field induced by this charge separation. Exactly. So what will happen though is the induced electric field will have exactly the same magnitude as the external electric field, such that the total electric field on the interior will remain 0. Exactly. So what has to be true is that no matter what the condition is, the total electric field on the inside of the conductor must be equal to 0. Okay. Now, what else? Number 3, the electric field lines which come from a conductor, like in the first case where it has charge all over in the exterior, must be perpendicular to the surface of the conductor. So what does that mean? So that means that what? If I have a conductor, let's say here's my conductor. And again, let's say this thing has charge on the outside of it. So here's all my charge. So that this thing is creating an electric field. What this thing is saying then is that all the electric field lines which come from the surface of this conductor must be perpendicular to the surface of the conductor. So at every location, there's an electric field line. This has to be perpendicular to the surface of the conductor. Why is that? Well, it turns out that this is true because let's say that my electric field lines actually came out at some parallel direction. So let's say that this electric field actually pointed in this direction. What would happen in this case? What would happen in this case then is since they're all coming out in some parallel direction, these charges would then feel a force in the direction of this electric field, which means they would start to actually rotate. Once they start to rotate, which means they would feel a torque. They would continue to feel a torque until the electric field only pointed perpendicular to the surface, at which point the torque would stop, which means the charges would stop rotating, and then it would become stationary so that all the electric field lines would then be perpendicular to the surface. So again, if I had some sort of parallel component, that's going to manifest itself as a force in this direction, causing them to rotate, meaning that they're going to feel the torque. They're going to start to rotate around until the electric field becomes perpendicular to the surface, at which point the torque would go to 0. In that case, everything would become static. Okay. So all this tells me then is that the electric field must be perpendicular to the surface of the conductor at every single point. There cannot be an electric field inside of the conductor, and all the charge must be on the surface of the conductor. One more thing we can learn. The last thing is what happens if I put a charge inside of a cavity inside of a conductor. So what does that mean? So that means, let's say, here's my conductor again. Here is a cavity inside. So I put a little hole inside of here. And then I put a charge, let's say, in the interior of this cavity. What would happen in this case? Well, what happened in this case is, number one, this is going to create his own electric field. So he's going to create electric field lines which point radially away, which means there'd be an electric field present inside of the conductor. Now, what's a conductor going to do? Again, since the charges are allowed to move freely inside of the conductor, what they want to do then is shield this charge by allowing all the negative charges then to move close to this positive charge to basically shield him. So on his interior wall, what's going to happen then is I'm going to build up a whole bunch of charges, which are then going to be negative charges. Meaning that if this thing had a charge of, I don't know, let's say 3Q, then I'm going to build up a charge around it of then negative 3Q. So the charge here will then match the charge here, just opposite sign to shield inside of here. Now, since all these negative charges have moved here, that leaves excess positive charges on the outside. So then I'm going to get a whole bunch of positive charges built up on the external wall. So that on the outside, I'm going to have a 3Q worth of total charge on the outside. Now, what happens though, again, is since I have a charge separation, positive charges here, negative charges here, I'm going to create an electric field induced inside of the conductor, which then points in the opposite direction as this electric field created by this charge on the internal. So this is, again, what we call the induced electric field. Now, as Jackson told us rightfully earlier, the same thing happens here. The magnitude of this induced electric field matches then the magnitude of the electric field created by the charge on the interior, which means that, again, inside of the conductor, the total electric field then must be equal to 0. Okay. So basically what will happen is if I put a charge in the cavity on the internal of a conductor, the external of the conductor will look exactly the same charge, which is on the interior. So again, if I put 3Q worth of charge on the interior, if I look at the conductor from the outside, I'm going to see 3Q worth of charge. But again, what happens is I have a whole bunch of excess charges on the outside, excess charges on the inside, creating 0 net electric field on the interior with the charge of the same magnitude as the conductor itself within the internal portion of the actual conductor, where the total electric field on the outside will actually be resonating from this charge on the inside. So the last part is number 4, for an internal cavity. With charge, the conductor will still have electric field total equal to 0 within, and on the outside or on the surface, a charge equal to the charge within the cavity. So these are all kinds of beautiful things we can learn about conductors. Right? So with a conductor, again, it has to have 0 electric field on the inside. If it has excess charge to it. All that charge has to be on the surface. The electric field has to be perpendicular to the surface, otherwise it would feel the torque. And if it has a cavity, the electric field on the inside is still equal to 0. But on the outside, we would see the charge, which is inside of the cavity. So it would resonate with an electric field equal to whatever the charge is on the inside of the cavity. Okay? A lot of fun stuff. One more thing to talk about in this chapter, and then we're done. So the last thing we're going to talk about in this chapter is what's known as an electric dipole. So that beautiful thing we drew yesterday, let's actually talk about it today. So let's talk about an electric dipole. So what's an electric dipole? So an electric dipole is actually two charges of equal and opposite charge, meaning I'm going to have a positive charge here and a negative charge here, where this one has a charge of, say, Q, this one has a charge of negative Q. So they're exactly the same magnitude, but opposite in sign. And they're separated by a spatial distance of d. Okay. Now, this is what we call a physical dipole. So what this does then is it creates an electric field where that electric field points again from the positive charge to the negative charge. So we get an electric field that points this way. But from here, we can define what's known as a magnetic moment, which actually points in the opposite direction as the electric field, which is what we're going to call P. So P is what's known as the electric dipole moment. So P then is equal to Q, which is the charge of the positive charge, times D vector. So what's D vector? So D vector is a vector which points from the negative charge to the positive charge, which has a magnitude of the length of the distance between the two charges. Okay. So basically here, all I'm going to do is draw a vector in this direction. So this is what I'm going to call the D vector, where the magnitude of D vector is simply equal to D, which is the distance between the two. Okay. So Q here, again, is the magnitude of the positive charge. And D here is the vector pointing from the minus charge to the plus charge of length. That's what we call the electric dipole moments. Dipoles are, of course, very important in things like chemistry, right? Water is an electrical dipole. In that case, the charge separation between the positive and negative charges, negative of the hydrogen, positive of the oxygen, but etc. So these are all electric dipole moments. Now we're going to be interested in is what happens if I put an electric dipole moment into an external electric field. So let's find out what happens if I put this guy in an external electric field. So let's say I have an external electric field. So here's my electric field. Say pointing in, and draw horizontally. Let's do it this way, make it a little easier. So let's say here's my external electric field, and I'm going to take my dipole. Here's my dipole, and I'm going to put it into my external electric field at some angle theta relative to the external electric field. And what we want to know then is what happens to this dipole? What happens to it? So let's think about our dipole. So again, our dipole is actually a negative charge on this side and a positive charge on this side. Right? Now, since I have charges in an external electric field, what must they feel? Based on where we started this class. A force, right? So what I know is there's going to be a force on this guy and a force on this guy. Okay? Now, for the positive charge, I know then the force is going to be in exactly the same direction as the electric field itself. I'm going to call that guy F positive since it's a positive charge. Now, for the negative charge, what's the direction of his force? Good, opposite direction as the electric field. So his force is going to be in this direction. So I'm going to call that guy F minus. Okay. So from here, I can ask the question, well, is there a net force acting on the system? So we can then say that the net force which is equal to the sum of the forces, is then going to be equal to, let me choose this as my positive x direction. So I'm going to have my F plus minus my F minus. Now, based on where we started off today, we know the force then is simply going to be equal to the charge times the electric field, minus then the charge times the electric field, where I'm going to ignore that negative sign because I already took the negative sign into account when determining the direction. But what's true about the two charges? They're the same. What's true about the two electric fields? They're the same. So this thing actually feels no force. So if I put a dipole into an external electric field, it doesn't feel a force. So what does that mean? That means if this is my dipole, this thing is being pulled in this direction. This one's being pulled in this direction, but it's being pulled such that it doesn't feel a net force. So what does that mean? It just means it's not accelerating, right? Remember, to have a force or a net force, there has to be an acceleration, which means it's not going to accelerate this way, or it's not going to accelerate this way, but it is going to do something. And what's it going to do? If I pull on this one this way, pull on this one this way, what is this thing going to do? Exactly, it's going to rotate, okay? So this thing's not going to feel a force in the fact that it's not going to accelerate this way or this way, but it is going to feel this. It's going to rotate, right? What do we call that? Starts with a T. Torque, right? So this thing is going to feel a torque. So let's talk about the torque that's going to happen on this guy. So this thing is going to feel torque. So there is no force. There is no net force, I should say. But it will rotate and feel a torque. So we now want to know, what is the torque that this guy's going to feel? So let's start off with the net torque. So our net torque then is going to be the torque from the positive plus the torque from the negative. So let's talk about what this thing is going to do. So remember that torque, I think we wrote this down before, but just to remind you, torque is equal to the length of the moment arm times the magnitude of the force times sine of the angle between the two of those. So if this was my R, this was my F, then this is the angle between the two. Now let's look at the positive charge first. In this case, this thing is going to rotate about its middle point, which means the length of the moment arm then is just going to be half the distance d between the two. Okay with this? So this is going to be d over 2. The force we know is just going to be q times e, if that's the force. But in this case, my moment arm is going to be what? Drawn a different color. This is going to be my arm. So I'm going to point in this direction. This is my r vector, which means I extend that, it's going to point in this direction, which means then that this is the angle theta between the two. Notice this angle theta here is exactly the same as this angle theta here, because the force is parallel to the direction of the electric field. R points off in this direction, so this angle here is the same as this angle. So since they're separated by an angle of theta, so this is then going to be written as simply sine of theta. And we'll talk about the direction of the rotation as well. For the other one, moment arm is this direction, right? Which means it's going to be the same distance. So it's d over 2 again. The force is still QE. It's still QE. The angle is still going to be exactly the same angle, because again, if I extend this guy in this direction, that's the same as this angle here, but these are alternate interior angles. So this angle is the same as this angle, which is the same as this angle. Now remember, torque has to do with rotation. So this one wants to rotate in this direction, which would be the what? Clockwise direction. This one also wants to rotate in this direction, so they both want to rotate in the clockwise direction. So since the two rotations are in the same direction, I'm going to add these two guys together, right? They're not counter directions from each other. They're rotating in the same way. So I'm just going to add those together. Now, since this thing is exactly the same as this thing, if I add this guy to him, the only thing that's going to happen is I'm going to end up with a factor of 2, which is going to drop to 1/2. So what this thing says is that this is going to be then equal to q times d times e times sine of the angle between the two. But what's q times d? P, it's just the dipole moments. So this is the same thing then as the dipole moments times the electric field times sine of the angle between the two. Yes. Yeah, it's possible to pull it apart. It would take a huge electric field, but yes. Yeah, you can actually pull that guy apart. Okay. Now, this guy is usually written as a cross product. I can do the same thing here. If you don't like cross products, that's fine. I'm just going to write what it looks like as a cross product. But this is the same thing as P cross E. So if you've seen torque in terms of a cross product, great. If not, just note this. So the torque on a dipole moment is simply equal to the dipole moment times the electric field times sine of the angle between the two. Now, it turns out that there's an energy associated with this, meaning that there's a potential energy associated with the fact that I rotate. So the energy associated with it, which is the potential energy, sorry, P, potential energy then is, turns out is equal to negative the dipole moment times the electric field times cosine of the angle between the two. So this is the energy associated with it. So what does this energy mean? So what this energy means is what? Let me use my ruler here. Okay, so in this case, let's say my electric field points in this direction. This is my dipole moment. Let's say this is the positive charge, this is the negative charge. So what this thing is saying is what? If my dipole moment is anti-parallel to the electric field, it simply has a potential energy of the dipole moment times the electric field. Then if I rotate it so that it's perpendicular to the electric field, it now has a potential energy of 0. And now if I let it go aligned with the direction of the electric field, it now has a potential energy of negative of the dipole moment times the electric field, because cosine of 0 is simply 1. So that means that this configuration has the greatest amount of energy. This has the least amount of energy, and this is halfway in between the two. So what's going to happen then is if I put a dipole moment into an external electric field, what it wants to do is rotate itself to make itself parallel or aligned with the direction of the electric field. This is the preferred direction in which it wants to be, because this is the least amount of energy. So if I take my electric field like this and I put it in here sitting like this thing's going to feel a torque rotate around until it does this. Effectively, this is what an MRI is. If you ever had an MRI before, it's the same idea, except it uses magnetic fields with magnetic dipole moments instead of electric dipole moments, but it's the same concept. So what you do is you actually put somebody into a huge external magnetic field, and what that does then is it causes the magnetic moments inside of the body to rotate to point in exactly the same direction as the external magnetic field. As it rotates, it changes energy. So what the MRI does is it actually measures the change in energy due to the rotations of each one of the individual magnetic moments inside of your body. From those energies, you can then create an image, which is where the image comes from an MRI. Right? This is the same concept. So this dipole moment wants to always align itself with the external electric field. So the energy comes from the rotation that it takes to rotate this guy around. So good. So let's do a couple examples of this, and then I'll bring up a couple group assignments so you can maybe stare at them for a little bit. So let's see what happens. Not this one. Number 8. There we go. So this one says that in this figure, we have a dipole moment. So that's this. Swings from an initial configuration where it is 20 degrees above the horizontal here to a final orientation. So it's 20 degrees below the horizontal here. And then it wants us to find the change in potential energy going from the initial configuration to the final configuration if the dipole moment has a magnitude of 1.6 times 10 to the minus 27 coulomb meters, and the external electric field is 3 times 10 to the 5th newtons per coulomb. So let's draw our picture. We'll work on this. Right there. Let's do this. So this is my electric field. My electric field points in this direction. So this is E, okay? And actually, sorry, I had it backwards. So initially my dipole moment points down in this direction. So this is my initial dipole moment at an initial angle of theta initial, where theta initial is 20 degrees. Then it's going to swing up to now this side. So now it's going to point this way. So this is going to be my final dipole moment, where it now swings up to a final angle theta final, which is then equal to 20 degrees. Okay. And again, what I want to know is, what is the change in potential energy to bring it from that one configuration to the new configuration? Okay. So in this case, we want to know, again, what is our change in potential energy? So let's talk about this. So our change in potential energy is going to be equal then to our final potential energy minus our initial potential energy. So remember, change is always final minus the initial. Now, using potential energy, which of course I just conveniently erased because that's what I usually do, we know that the potential energy is negative the dipole moment times the electric field times cosine of the angle. So let's put that in. So it's going to be negative our final dipole moments times the electric field times then cosine of the final angle. We'll talk about what that is in a second. So let me call that not theta, call it something else, call it phi for now. Minus a minus, which gives me a plus of the dipole moments initially times the electric field times cosine of the initial angle. Now, the reason I'm calling these phis instead of thetas is because remember that this angle here, just like the angle in the torque, is the angle explicitly between the dipole moment and the electric field, which is not the angles I gave you here. So my final angle then, this final angle is actually this angle here. This is actually theta final, or phi final, I should say. And then this angle here between the electric field and the dipole is the initial. Okay. Okay. So in this case, phi final then is going to be, well, this is 90 degrees and this is 20 degrees, then this angle then has to be 70 degrees. And phi initial then is going to be, well, again, if this is 90 and this is 20, then phi 110. Good. Yeah. So this is going to be equal then to negative P times the electric field times in cosine of the final, which is 70 degrees, plus P times the electric field times cosine of 90 plus 10 or 20, sorry, which is 110. There we go. Plug in my numbers. What I find in this case then is, this works out to be 2.4 times 10 to the minus 4 Newton meters, if I'm looking at the right problem. No, I'm not looking at the right problem. It's actually negative 3.28. Positive 3.28 times 10 to the negative 21 joules. Sorry, looking at the wrong problem. It's okay. Now let's talk about the sign here. Actually, no, it is a negative. Sorry. It is a negative. There we go. Okay. Now the other question I can ask from this is, what was the work done? So I could also ask, what was the work done? So remember, work is equal to negative the change in potential energy. So in this case, if I was asking what was the work done, then the work in this case would just be negative of this number, which would then be the 3.28 times 10 to the minus 21 joules. Okay, so this would be the work done. Now just talk about this work for just a second. In this case, since the work is positive, what that means then is that the electric field itself did the work. Okay. Which makes sense in this case, because as we talked about earlier, what it wants to do is it wants to rotate the dipole so that it becomes parallel to the direction of the electric field. In this case, it's rotating from 110 degrees down to 70 degrees, which means it's making it more parallel, which means the electric field itself did that because it wants to move it so it's parallel to the direction of the electric field. If it did the opposite, meaning if it went from 70 degrees out to 110 degrees, in that case, the work would be negative because the electric field didn't move it going from here to here, something else moved it. And that would have to be some sort of external agent. So the sign that shows up on the work tells you who did the work onto the system. Right? If it's a positive work, what that means then is that the electric field itself did the work. But if it turns out to be a negative work, that means some external agent did the work instead. Right? My brain is up because this will be something that shows up on the next exam. I'll ask you a question of who did the work. And the way you determine who did the work, again, is that you look at the sign of the work. If it's positive, it means that that agent, in this case, the electric field did the work. If it's negative, that means something else had to come in and physically do it. Okay. We'll talk about this again as we actually get there. So, everyone okay? So these are dipoles. So not too bad. So good. So that brings us to, now we're finally done with this chapter. We only got a couple minutes left. Oh, not too bad. We got about 9 minutes. So let's talk about our next set of group assignments. So you can work a little bit on these today and then finish them off later. But anyways, first one's nice and easy. So this one says that we have two charges. We have Q1, which is a distance R1 above the origin on the y-axis, which has a magnitude of 10 microcoulombs, a positive charge. On the x-axis, which is some distance R2 away from the origin along the x-axis, has also a positive charge, which is 13 microcoulombs. So the first thing the problem wants you to do is use the things we talked about yesterday, which is the electric field lines, and try to draw what the electric field should look like throughout the entire space. So again, this is positive charge, radiating electric field lines, radiating electric field lines. What should it look like? Once I do that, part B then is to calculate the value of the electric field specifically at the origin. So at the origin right here, this is our point P. What is the value of the electric field, both magnitude and direction? And so using the superposition principle. And then part C is using what we just talked about today, which is now that we know the value of the electric field, we're going to put another charge, Q3, exactly at the origin. What's the force on Q3 based on the fact that we know the value of the electric field? So that's just all the stuff we started off with today. So now that we know the electric field, we can find the force on that particle. So that's this one. So this one's pretty kind of quick and easy. Not too bad, just getting used to all the things that we've been talking about. So that's the first one. Let me talk about the second one real quick, and then I'll let you play. Let me start working on these. So second one has to do with parallel plate capacitors, of course. So this says, suppose electrons enter a uniform electric field midway between the two plates. So these two plates are separated by a distance of 1 centimeter. This enters at the midway point. So this is 0.5 centimeters away from the top plate. At an angle of theta initial relative to the horizontal. So then it says that the path is symmetric, which means that this electron is going to come in, it's going to curve, just misses the top plate, and then turns around and then comes out on this side. So it comes out at exactly the same angle theta initial that it came in at. So that's this part here. So it just barely misses the top plates. Right. And the value of the electric field is 3.8 times 10 to the third newtons per coulomb. And the length of the plates is 6 centimeters. So what I want you to do from here is using the fact that you know it just misses the top plate, which means that the distance it travels in this direction is half a centimeter. And the value of the electric field, and that this is electrons, so you know the mass and you also know the charge. What then is that initial and final angle that this thing comes in at and leaves at? So here you're basically just looking at projectile motion and all that kind of good stuff. Now, easiest way, I won't lie to you, to do this problem is actually use the range equation. So if you have seen the range equation, you can use that. If you have not, you can still do it all the same ways that we did the problems today. Just take a couple more lines of algebra, but the quickest way to do it is actually just using the range equation. But I know Dr. Merlot usually doesn't talk about the range equation, so if you had Dr. Merlot, you probably haven't seen it. My 175, I will talk about it a little bit, but then tell you only use it if you know how to use it, which means it has to be exactly like this, start and finish on the same horizontal line. But other than that, again, if you've seen it, great. If not, you can still do the problem without it. So you still get the same result at the end of the day. So again, all you're looking for is what is that angle. So these are already up on Blackboard, but I'll bring up the first one so you can work on that one for a little bit, whatever time we got remaining. So we got about 5 minutes. We'll talk about it a little bit and then go from there. Other than that, tomorrow we'll start chapter 17, which is the second chapter for the upcoming exam. And yeah, we'll go. As always, I'm covered in chalk. Haven't seen you guys at the gym lately. Gotcha. I decided not to go today. I just slept in. I'm kind of beat up for a little while. That's right. Good. Yep, that's right. Good. What's that? That's why I just draw blobs these days. But I used to care about drawing, but now I just don't. What's up, Dave? Yep. Oh yeah, it can come closer to one side or the other. Yes. Yeah. Well, for the first one, it didn't really matter much. We were just looking for the deflection. But the second one, we specifically wanted it to be at the bottom because we wanted to see the top one. But yeah, like the one I gave you today came in, or for the group assignments, exactly halfway. But yeah, it doesn't really matter. Yeah, it's just from problem to problem. It's going to be something different. Yeah. But the point is, no matter where it is on the inside, it still feels the same acceleration because that electric field is constant everywhere inside. So yeah, so it doesn't matter if it's at the bottom or the midway point or something else, that acceleration will always be the same at any point on the interior. So that's the most important thing to know about it. So all right. Okay, Ryan.
I'm working on it.
There you go. They'd have electric fields there. Yeah, because here we don't know, because we're only looking at the electric field, but you're absolutely right. Since they're both positive charges, this one's going to have an electric field downward, and this one's going to have one to the left. Exactly. So electric field, yeah, would be that direction. Exactly. Yes, exactly. Now the force will be in the same direction, but since it's a negative charge in this case, it's going to be in the opposite direction due to it being negative because it rotates by 180 degrees. But yeah, so Q3, once you put in Q3 at the origin, it's negative charge. So it's just going to be like opposite. Exactly. Gotcha. But yeah, when I'm talking about the field itself, you're absolutely right. Yeah, it's going to point down in that ish direction. Overall direction will depend on the distances, magnitudes, and all that stuff. But yeah, exactly. What's up, Javen? Exactly. Yeah.
Exactly.
Exactly, because they're both positive charges. So So they only originate on each one of those, and the only place they can terminate is at infinity. So exactly, they're going to move in and do something like that. So they're going to diverge away from each other. Exactly.
And how many of these do you want? You want just the main one?
It's just, yeah, maybe,
Just a few.
yeah, put a few coming out of each one. Because again, it wants for the whole space. So just, yeah.
Try to cover white space.
Yeah, just kind of put in a few, just to kind of say, okay, this is what it's going to look like, and a few different regions. You know, you draw 1 or 2 out here, and some curving down in this direction as well. So, yeah, doesn't have to be
Perfect.
yeah perfect or filled in everywhere, so I can't see anything. What's up? K is 9 times 10 to the 9th Newton meter squared per Coulomb squared. Yep, that's right. And that's 1 over 4 pi epsilon naught, if you want to know that portion of it as well. But numerically, it's just 9 times 10 to the 9. Yeah. Probably the easiest way to look at it. All right, so we're officially done. So I'll see you guys tomorrow. Tomorrow we'll bring in some more demos, more light shows. That would be great. Monday, so that's going to be the 18th. We're
Friday is the 15th.
yeah 18th because the last one was on the 11th. So yeah. You're welcome.